group A, and we need to. And
You're a reader.
Yes, I'm reader. I want to introduce the Earth destroying bomb. The Earth destroying bomb is an ultimate weapon that Doraemon always takes out whenever he encounters a mouse, but he has never actually used. And he claims that it could easily destroy the Earth. Okay, next. So now we need to know how much energy will it take to destroy the Earth. First, we suppose that destroying the Earth means blowing it up until it is completely shattered and no longer spherical. And we assume that the Earth is a homogeneous sphere with radius r, mass m, and density long. Okay, next. And U is a gravitational energy of this sphere. And du is minus gmm divided by r. And g is the gravitation constant. And we can integral du. And this is the spherical shell, mass of spherical shell, and this is the inner sphere, the mass of inner sphere, and we can get the answer. Okay. And we know that m equals 5.97 cross 10 to the 24th power kilogram, and R is 6.37 cross 10 to the 3rd kilometers, and we can get the gravitation energy is 2 cross 10 to 32 power joule, and it will take about the gravitation energy to completely destroy the Earth. And in this world, the most powerful bomb is the star bomb. Created by mankind. And we know that the power equals 2.1 cross 10 to the 17 power joule. And it is smaller than we get the answer before. So it is impossible. We can use the bomb to destroy the Earth.
Yep.
Okay.
Okay. Very nice. Good.
I want to introduce the hopter in Doraemon.
Okay.
The hopter is one of the most famous gadgets in Doraemon, and it is simply to use. Just wear it on your head, and you can fly anywhere you want. And before the calculation, I want to introduce the word lift force. Lift is the upward force that helps object to overcome gravity. And for example, the airplane wings generate lift by creating the pressure difference between the top and bottom surface. And the hopter works on the same principle. Let's figure out how fast the hopter needs to generate vertical airflow to lift Doraemon off the ground. And we use the lift formula. The rho is air density, and the A is swept area of the rotor, and V is the vertical speed of the air. That is what we want to calculate. And to lift Doraemon, the lift force has to be equal or greater than his weight.
Right.
And here is what we know. The hopter diameter is 20 centimeter, and Doraemon's weight is 129 kilogram. And so we have M is 129 kilograms, and R is 1/10 meter. Rho is 1.225 kilograms per cubic meter. And to the lift to countergrade the weight, we have derived this equation. And after the calculation, we found V is greater than 256.3 meters per second. It's over 900 kilometers per hour. And it is impossible because speed is too high for human body to handle, and it would cause physical damage. So it is impossible to use in real life. And if we use it in real life, what did happen? The high-speed airflow will hit your skin and tissue, and it could tear them apart. And even if your body somehow survives, the tension on your scalp will rip your hair or even your entire scalp off, leaving the hopter flying away on its own.
Okay, excellent. Okay, so Jenny, this is excellent, but then if the program is the hopter, it's too small, no? So can you make it larger so that, can you come up with a design that so it works?
Oh, okay.
Maybe make it larger or put it in your body, something like that. Okay, excellent.
And next one, we want to introduce the third tool in Doraemon, the air cannon. And the air cannon in Doraemon is uses the compressed air to create a powerful blast that knocking down obstacles far from away or repelling enemies with the concentrated shock wave.
Okay.
Okay, so in the movie, Doraemon wants to use the air cannon to take down the T-Rex here to save these guys. And so we suppose the weight of the T-Rex is 5.6 tons, and the friction coefficient of the ground is 0.6. And we want to calculate the maximum static friction of the T-Rex and the formula here. So we put the value in the formula, we get the result is 32,928 newtons. So if Doraemon wants to use the air cannon to take down the T-Rex, the force from the air cannon let the gas, the pressure, the air thrust must equal or bigger than that value. That he can beat them. So, and we assume the radius of the air cannon is 0.1. So the cross section is 0.01 pi meter square. And we put all value into the formula. We get that the press it needed is about 10.34 atm. Okay, and then according to Newton's third law of the motion, the recoil force Doraemon receives will equal to the force emitted by the air cannon here. The picture here. So, and according to the official data, the weight of the Doraemon is 129.3 kilograms. And we suppose the mass of the air cannon is 10 kilograms. And we put all value in, use the same method to calculate the maximum static friction. The max static friction of the Doraemon is about 954.2 newtons, and it is less than the value that we calculated last page. So the iron will be pushed down far from away, not just standing there and shoot. Yeah. So if it follows the law in physics, it will roll. Okay. That's it.
Very good, Connie. Connie, so in your report, can you calculate what's the Doraemon speed?
Yes.
How fast?
Oh.
It's gonna roll away.
Okay.
Okay. Well, excellent. Very good, Connie.
Okay, I'm Joseph.
それは任せといてよ。いいか。お元気マンガズ。このカードを入れるだけでどんな天気も作れるんだ。見せて。それじゃあまずは曇りのカードを入れてみよう。はい。場所はひとまずこの部屋だけでと。ほら出てきた。面白い。正式には積乱雲。これが大きくなっていくと雨が。
So the weather box, the weather box is a device that can change the weather, and I want to know if I want to make a raining weather, how much energy does it need? So let's make some assumption. The temperature is about 20 degrees, and the relative humidity is 50%, and the area is about 100 kilometer square, and height is 1 kilometer. So we can calculate the volume. The raining volume we can calculate it equals 1 times 10 to the 11 square meter. So next. In case 1, I want to induce rainfall by increasing humidity. And first, the saturated water content at 20 degrees is about 17.3 grams per cubic meter. And when the humidity is 50%, it contains 8.65 water. So I can calculate the total additional water mass. It is about 8.65 and times the volume, and it equals 8.65 times 10 to the 8th kg. And second, I need to the latent heat of vaporization. So the latent heat is the energy absorbed or released when the substance change its phase. So and the latent of vaporization LV is about 2.26 times 10 to the 6th joule per kilogram. So we can use the thermodynamic equation, and it is about latent times the mass, and it is equals 1.96 times the 10 to the 15th joule, and it is a large energy. Thanks. Oh, okay. So in case 2, I want to use induce rainfall by just raising the temperature by 10 degrees Celsius. So the first thing I need to the total air mass. It is the air density times the volume. It's about 1.225 plus times the 10 to the 11th. And the specific heat capacity of the air is about Cp is about 1005 joule per kg Kelvin. So the temperature change is delta T is 10 degrees. So by the thermodynamic, we can use mass times the Cp times the delta T. It is about 1.23 times the 10 to the 15th joule. It's also very large. So in conclusion, by raise the humidity, we need to large energy, and it is about a 1 gigawatt thermal power plant operating in 23 days. And by the increasing temperature, it also needs to 14 days. So I think the weather box is its requirement of energy is too big to supply. So it is impossible in the real life. Okay, it is my report.
Very good. So I have a question. Why the second one? Why increasing temperature make a rainfall?
Sorry, again.
Why by increasing temperature you can make rainfall?
And I just assumption when the it needs rise the 10 degrees.
Mm-hmm. But does it make a rainfall?
In my assumption, it will rainfall. So
Okay. Can you explain that part in the report?
okay.
Because I thought you need to decrease the temperature to make rainfall.
Okay.
Because if you increase the temperature, then the air can take more water. And also the volume, you assume the very large volume, right?
Yeah.
Like 1 kilometer or something.
Yeah.
But in your movie or video, Doraemon is just creating this much crowd, no? So it's very much smaller than you assume.
The video just they will use the machine to the outside and add the weather rainfall.
Okay. Okay. Very good.
Thanks.
Very good, Joseph. Next, please.
Okay. My name is Jen,
Okay, Jen.
and okay, I'm going to introduce the small light,
Okay.
and let's watch the video first.
Who wondered how we can make it
That's
rain?
this.
Well,
Okay, next page. Okay, and in the video, Doraemon mentioned that the small light not only can let Nobita's body become smaller, but also can allow Nobita be as strong as original. Okay, next page. But there is some mistake in the video.
Okay.
So the first one is that if Nobita becomes as small as a fly, he will lose the fly. Because we suppose the normal Nobita's height is 1.7 meters and it weighs 60 kilograms. And we assume that the small Nobita will be 5 myometers. And we can calculate the shrinking ratio will be 0.00294. And first, we do the mass reduction, and we can get the smaller Nobita's weight is 1.52 milligrams, and it's as big as the fly. And we compare both of their muscle strengths, so we can get the strength of the small Nobita is 0.00432, and it's less than a fly, so Nobita will lose flight. Fine. Okay, next page. And the second mistake in the video is that the density of a smaller Nobita is impossible for a human. And we suppose Nobita's volume will change from V0 to V prime, and R is a shrinking ratio. And we suppose we can calculate the density will change from rho 0 to rho prime. And that's the shrinking ratio be 0.1, and we can calculate the density of the small Nobita is 1,082,000 kilogram per meter cubic. And it's impossible for a human density because a human density is about 1082. So it's too big. So it's impossible. So there is two conclusions in my calculation. The first one is Nobita will not win the flight in the flight because Nobita's muscle strength is less than a fly when they're in the same size. Okay. And the second one is it is impossible for a human to become smaller than a fly because of the density. Okay. And in a reality, if the people want to become smaller, we need the beam, and the beam needs to be capable to destroy atomic matters. And the second one is that electrons are not exactly anywhere and any motions because it is like anywhere here, and we don't know where is it. So we can't predict for certain where one will be orbiting. Yes. So it's impossible for people to become smaller. Yes, that's all my presentation.
Okay, excellent. Yeah. Very good.
Okay, thank you.
Okay, next is Alan.
I will introduce the superhuman global, and the superhuman global appears like a regular global, but what is grant the user immense strength, and I assume the acceleration need to make girls on concessions based on human data, and there are also some number I assume after I search on the just yes. And I using the Newton's second laws of motion and kinetic energy formula, and this is my F is equal to 10 at 10 pardon. This is my and just this and we and we need only the data show in both about can knock out the Guriel. Such power is impossible to exert in reality with just a small global. In reality, these people is cannot just knock out the global. I think it will die. Yes.
Okay, so is that so okay, good. Aaron, good. So can you compare this force and energy to, for example, Mike Tyson's punch or something like that? Yeah, the boxer, heavyweight boxer, or some punch of the bear or something like that. We want, instead of very large, we want you to compare numbers.
Oh, okay.
In your report.
Okay.
Okay. Okay. Good. Excellent. Okay. So you guys want to go quick? Okay, everyone joined? Hello. Please, Benson, hurry up. Did you share this screen online for online people? I don't see it. Right? Can you share it on the Google Meet so that online people can also join?
哦，给他们拼这个。那加入。等一下啊。
去找老师的信。
给你。
就是 Google Doc， 好的。
那个很多文件那个，就是点第一个。
这个吗？不然 YouTube。
就是
前面只
这
在开学。
Google Doc 它的 link。
对，就有一个文件。
传就这些了。
Yes, that's it. Wait, the presentation was not shared online? Sorry. I'm worried that the presentation was not shared online. I'm worried that the presentation was not shared online.
关静。
分享那个画面。
I'm a little bit scared to ask. Did you share your presentation online?
I think it's sorry.
You guys should remind. So the other group shared, right? Yes. Okay, good. Online people should speak up too. No? Okay, online people also please join. You guys join? Did you join? Okay. Then shall we start?
Okay.
So quick.
So the explanation is latency is the energy absorbed or released when the substance change its state, like boiling or melting, and without a temperature change. Okay.
Thank you. who's ABC? Oh, congratulations. Please report to the TA. I have a question. The second one is not to the cubic. Second question.
Oh, yes.
Is it just square?
It's proportional to.
Okay. Can you explain?
Oh, and it's the. Oh, okay. 你开那个 PPT。
Is it in a square?
看，这是帮我打开，这里打开，打开。它现在不能显示。它现在没有
要把它
显示。
它变成。
It's a scaling loss, and because the strength is proportional to it's a shrinking ratio, and it will be proportional to the shrinking ratio squared, because of the surface of the body. So it will be
okay.
yes.
Okay. Thank you.
Thank you.
Okay, thank you very much. You guys did very, very well. Yeah, I think you guys did very good.